This is Workbench with Workbench Quagmire, back with day 70 of our free code camp, Python certification in 100-ish days. We are going to continue through our theory sections here on algorithms with our section here called How Do Stacks and Queues Work? Stacks and queues are data structures commonly used in computer science. They're linear data structures that follow specific rules for adding or removing elements. Stacks, let's start with stacks. A stack is a last in, first out data structure. This means that the last element that was added to the stack is the first one to be removed. Stacks have two ends, which we know as top and bottom. Elements are added and removed from the top of the stack. You could think of a stack as a pile of dishes where you only place dishes at the top of the pile and take dishes from the top of the pile. So there's a stack. These operations of adding and removing elements have special names in this context. Adding an element to a stack is known as push operation. We say that we push an element onto the stack when we add it to the top of the stack. Removing an element from the stack is known as pop operations. We say that we pop an element from the stack when we remove it from the top of the stack. As you can see that we don't really perform any operations at the bottom of the stack, but we keep it there as a reference. The time complexity of the push and pop operations is typically constant time complexity. So a big O of 1. When you push an element onto the stack, the element is simply added to the top. When you pop an element from the stack, the element at the top is removed. Therefore, the time it takes to perform these operations remains constant regardless of size of the stack. The space complexity of the push and pop operations is usually constant. This means that the amount of memory required to perform these operations remains constant regardless of the size of the stack. Queues. Now that we know more about stacks, let's learn about queues. The queue is first in, first out, linear data structure. This means that the first element added to the queue is the first one to be removed. Queues have two ends, front and back. So elements that are added to the back of the queue and then they are removed from the front of the queue. You can think of this queue as a line of people waiting to pay for their groceries at the supermarket. The first person in line will be the first one to go to the cash register, while new people will join the line at the end. The operation of adding and removing elements has special names in the context of a queue. Adding an element to the back of a queue is known as in-queue operation. An in-queue operation, the new element is added to the end of the queue, becoming the end of the line. Removing an element from the front of the queue is known as dequeue operation. In the dequeue operation, the element at the front of the queue is removed and the next element in the line becomes the front becomes the new front. So dequeue, front. Time complexity of in-queue and dequeue operations is 1, constant time. The time it takes to perform these operations remains constant regardless of the size of the queue. The space complexity of in-queue and dequeue operations is usually constant. This means that the amount of memory required to perform these operations remains constant regardless of the size of the queue. Stacks and queues are data structures used in computer science for organizing and managing elements. Understanding them is essential for building efficient algorithms in various programming applications. So here's our quiz. What is the primary difference between a stack and a queue? A stack is last in, first out, while queues are FIFO. That's true. Stacks are FIFO. That's not true. Stacks are used for storing data, while queues are used for processing data. That's not true. There is no difference between stacks and queues. That's not true. So number 1 is our best choice. Which operation is used to add an element to a stack? We push, we pop to remove it, and then these are queue operations. We put something in a queue, we take it out. Which operation is used to remove an element from a queue? That would be the dequeue. There we go. All right. Go to our working with common data structures. How do singly linked lists work and how do they differ from doubly linked lists? A linked list is a linear data structure in which each node is connected to the next node in the sequence. These connections create a data structure that looks like a chain of nodes. where each node stores data in reference to the next node in the linked list. So we use these references to go from the first node to the next node and so on. Linked lists are commonly used for implementing other data structures such as stacks, queues, and dequeues. They can also be used to implement essential graph algorithms such as depth-first search and breadth-first search. I don't know what either of those are. I think we've covered them. Singly linked lists. A singly linked list is a type of linked list in which each node is connected to the next node in the sequence. Each node is connected to the next one by storing a reference to it. This single reference per node allows you to traverse the linked list in one direction from start to end. The search can only move forward, not backwards. In this example, you would start at the end of the node, head node A. The head node is the first node in the linked list. In a singly linked list, the head node is usually the only node that is directly accessible. This is where the search process will start when you're trying to find a specific node. The process will start with node A, then it will continue to node B, node C, and finally node D, the tail node. It may also stop before that if you implement a specific logic in your code. The tail node is the last node. It is used to determine when the process has reached the end of the linked list. Inserting nodes. One of the great things about linked lists is that they do not have fixed size. They can be expanded or shrunk as needed by simply updating the connections between the nodes. You can insert a node at the start, middle, or end of the linked list. Linked lists don't necessarily need to store the nodes in a specific order. The order will be determined by the connections between the nodes. However, if you do need to keep the nodes in a specific order for a particular use case, you can do so by implementing that logic in your code, and the criteria you implement will determine if the node is inserted at the start, middle, or end. To insert a node at the start of a linked list, you just need to create a connection between the new node and the node that used to be the head node and make the new node the head node instead. This is an example where we insert node E at the start and make this the new node, the head node of the linked list. Inserting a node at the beginning of a linked list has a constant time complexity of 1 because it only requires updating the reference to the head node and connecting between the new head node and the next node in the sequence. In this example, we are inserting node E at the start of the linked list. This will work correctly. But if we want to keep the linked list sorted in alphabetical order, node E would have to be inserted at the end of the linked list instead. To insert a node at the end of the linked list, first you need to reach the end and then add a connection to the new node to make it the new tail node. The operation has linear time complexity n, where an n is the number of nodes stored in the linked list because the first you need to reach the end of the linked list to make the insertion, and this would require going from one node to the next, so on until the end is reached. If the node is to be inserted somewhere in the middle of the linked list, the connection between the nodes will have to be updated too. The previous node in the sequence should be connected to the new node, and the new node should be connected to the next node, like the following diagram. The insertion operation is a constant space complexity of 1, since the inserting a new node only requires creating it and updating the connections between the nodes. The operation doesn't depend on the size of the list itself. Removing nodes. Just as you can insert nodes, you can also remove them from the start, middle, or end of a linked list. To remove the node from the start, you just need to update the reference to the head node, which should be the next node in the sequence. This operation has a constant time complexity of 1 because it only requires updating the linked list reference to the head node. To remove a node from the middle of the linked list, you need to update the reference of the previous node to connect it to the next node in the sequence, forming a sort of bridge between them, as you can see in this diagram. That will remove the node that you want to remove, in this case node B, from the sequence of connections, so it won't be reached the next time you traverse it. To remove a node from the end of the linked list, you need to remove the connection of the previous node and to make this node the new tail node. Now the linked list will end at the new tail node. This operation has a linear complexity of n because first you have to reach the end of the linked list. The deletion operation has a constant space complexity of 1 because no additional memory is required to delete a node. A doubly linked list. Now that we know more about singly linked lists, let's talk about doubly linked lists. A doubly linked list, each node stores 2 references, a reference to the next node and a reference to the previous node in the sequence. This means that a doubly linked list can be traversed in both directions. In this type of linked list, you also common to keep a reference to the tail node in the linked list itself to start the traversal from the end if necessary. That sounds great, right? More flexible than a singly linked list. However, doubly linked lists require more memory than singly linked lists because each node stores 2 references instead of 1. This is something you need to keep in mind when you're choosing the right data structure for your project. There is a trade-off. The insertion and deletion operations work exactly the same. The only difference is that now you will need to update 2 references per node, keep track of the reference of the tail node to insert elements at the end of the doubly linked list very efficiently, and start traversal process from the back if necessary. Singly and doubly linked lists are essential data structures in computer science used for storing and manipulating elements in sequential order. Understanding your differences is essential for choosing the right one for your specific application. So, what is a linked list? A data structure that stores elements in a continuous block of memory. A data structure where nodes are connected using references. A data structure that is always sorted. A data structure that has a fixed size. So, I think it's choice 2. What is the difference between a singly linked list and a doubly linked list? Singly linked lists have a head and tail node, while doubly linked lists do not. That's not true. Singly linked lists can only be traversed in one direction, while doubly linked lists can be traversed in both directions. That's true. Singly linked lists are more efficient to insert elements at the end, while doubly linked lists are more efficient for inserting elements at the beginning. I don't think that's true. Singly linked lists require more memory. That's not true. So option 2. What is the time complexity of inserting a node at the beginning of a singly linked list? I believe it's 1. There we go. All right. Well, with that, we're going to conclude our session here on these theory sections for algorithms. Next time we'll tackle this. Let's see. I think we just got the one left. Yep. It's got the one left, but it looks like a pretty good one. So thanks for watching the video. Don't forget to comment, like, and subscribe, and I'll see you next time for day 71 of our free code camp, Python certification in 100-ish days.